Hello, everybody. And this is section 4.5 of Calculus 1. You will see that this section has to do with graphing and differential calculus, right? Now, behind me is a virtual background picture, and I choose, from among a few choices I have. All of these pictures have been created using my app called Good Grapher, one word, Good Grapher. And it is a tremendous tool. I have referred to it a couple of times in my lecture, but I strongly encourage you to download it and then try to use it to graph different functions. Of course, in the background, what I am using is three-dimensional graphing feature, but you can do the 2D graphs in this class, and you will see that this is actually going to help you a lot as you grasp what graphs are going to look like for various functions. All right, so you'll see a lot of graphs in this section. And so let's look into section 4.5. All right, so in this section, we are going to learn the relationship between derivatives and the shape of a graph. Okay, I have already drawn several graphs here. Let's look at each of these. All right, the first one looks like we have a constant function. Not very exciting. Now you know what the derivative is here for all x, and that is 0, right? So we have already learned theoretically in the last section that if the derivative is 0 over an interval, then the function has to be a constant function. The second one we see here is a line function, mx plus b, a linear function. And in this case, of course, m appears to be positive because it's going going up as you go to the right. Here, the derivative, whoops, I guess I should be writing down here. The derivative is m, and it's constant, right? So when the derivative is constant, then you would expect the function to be a linear function. All right, now I have 4 more pictures here. Notice here, in the first 2 graphs, the function is increasing, right? And that means that the derivative is positive. Okay, but there is a difference between these two. If you look at the way the derivative is increasing, let's pick a few points here like these, right? The first, the slope of the tangent line seems to be kind of a small number, and then becomes like closer to 1 and then gets bigger than 1, right? So you can tell that the derivative itself is increasing as you go from left to right. I think you can easily see, and we will restate this more carefully later, but the second derivative is also positive because it means, well, because what this means is that the derivative itself is increasing, meaning that the slope gets steeper and steeper, or the derivative gets bigger and bigger. Over here, the function is increasing, which means the derivative must be positive. But if you look carefully at these points again, the derivative started out with a pretty high number and then starts to get less and less and gets closer to 0, right? So you can see that the second derivative is actually less than that. And if you look carefully, imagine yourself driving a car as you go this way, right? You're slowly turning left, but over here, you're slowly turning right, okay? And this whole idea is called concavity, which we will be visiting in just a few minutes, okay? So keep this in mind. I think this car steering or bike steering, if you are not old enough to drive, is actually a good metaphor in understanding concavity. All right, now over here, you're still turning to the right, just like the last one, but this time the derivative must be negative, right? Because it's decreasing. And then what's happening with these negative derivatives? It started off with like maybe negative 0.98, whatever. It becomes -1, and pretty soon it becomes -2. So the derivative itself is going down, decreasing, right? So it looks to me like the second derivative is also negative, okay? Which means it's decreasing. And then finally, we have a decreasing function here. So the derivative stays negative, okay? But if you look really carefully at the shape, here's the shape of the graph. The derivative used to be maybe -2 and then -1 and then between -1 and 0. So even though they stay negative, the derivative seems to be increasing, not the function itself. A function is decreasing, but the derivative seems to be increasing. So depending on the first and second derivatives, you see 4 different cases of smooth curves, right? The first one was a horizontal line. The second one was a linear function. And whenever you have these curves, then you have 4 different situations. Okay, so that kind of summarizes everything I'm going to say in this section, actually. All right, I'm going to draw another picture, and then you can tell me about the first and the second derivatives at each part. All right, so I know this is a lot to digest here, but let's take a look at what's happening in this graph of f. Okay, as you go from here to here, right, what's happening in this interval? Well, the derivative is positive, and the second derivative seems to be positive, right? Because you are going up higher and higher. So if the rate of increase itself is increasing, that means the second derivative must be higher. Okay, what's happening at this point? Right at this point, the derivative does not exist. You see why? There is a sharp point, okay? And whenever you have a sharp point, not a smooth function, then that derivative does not exist, okay? Because it seems like there's a discontinuity in the derivative itself, right? Okay, so then this part here, this interval, the function is decreasing. So the derivative is definitely negative. And how about the second derivative? Okay, we have actually what we considered in the last case here. It is decreasing, but the amount of decrease is getting less and less, which means that the numbers, the negative derivatives are becoming closer to 0, which means it's increasing, right? So the second derivative is positive here. Another way of saying this is it's concave up, okay? Because you're turning or you're steering to the left as you drive. And then here, you're still steering to the right, left. So the second derivative is still positive, meaning that, so here you can see that the function is increasing, meaning that the derivative, it must be positive, just like the first case, right? In the first interval, you had the same situation. Both of these derivatives are positive. Now, something happens at this point, okay? Now, we will be talking about this, but it's called a point of inflection or inflection point. Soon to be discussed also or introduced formally. All right, this is the point where as you have been driving here, you are steering to the left, and then right here at this point, you stop steering to the left, you are moving your steering wheel back to the center and then starts to go toward the right, okay? So this is a particular point. We will right now just call this inflection point, because that is the name officially given to this. What's happening here at this point, the derivative is actually still positive because it's increasing function, but it turns out the second derivative is 0, okay? It goes from, in this case, positive to negative. Over here, the first derivative is positive because the function is increasing. The second derivative turns out to be negative because it's increasing, but at the slower rates as you continue to go to the right. All right, now at this point, it appears that the derivative hits 0, okay? Because there's a horizontal tangent, just like you see in that x cubed function at the origin, all right? But still, from here to here, it's, maybe I should have spread this more. The derivative is still positive because in this interval, the function is increasing, and not only is it increasing, it seems to be increasing faster and faster. Again, what happens in this first interval and the third interval happens to be again in this fifth interval. And then the sixth interval here, the derivative is negative because it's going down, and it's going down faster and faster as you go to the right. So the second derivative is also negative. And after that, the function itself is still decreasing, meaning the derivative is negative, but then the rate of that decrease is slowing down. So the second derivative must be positive. All right. So you can tell, I mean, this is a lot to digest here at the beginning without me telling you anything ahead of time, but I think you can easily understand these things. The first and the second derivatives actually give you a lot of information about the shape of the particular graph. All right, so with that as an introduction, let me explain to you this is actually a theorem, but this theorem has a name, a specific name. It's called the first derivative test. There will be a second one. That's why it's called the first derivative test. Also, it's called the first derivative test because it uses first derivatives, all right? If f is differentiable, now if you look at the book, because our textbook authors have to be like extremely careful, right? Just a little small mistake they make on one page, and then they'll hear from hundreds of readers and teachers and instructors and scholars because it's in print. And so whenever an author of a book, textbook in particular, writes, they have to be extremely, extremely careful. So if you look at this theorem in the book, it has a slightly different, much more careful hypotheses. Like they will say, if f is differentiable, let's say on an interval from A to B, an open interval, and let's say if C is a critical point, critical point of f on I. And what the book says is that f doesn't have to be differentiable at the critical point. Meaning, you see do you remember what a critical point was? Where the derivative is either 0 or undefined. Well, I said f is differentiable, so f prime of C not being defined is not a possibility because I said it's differentiable. But actually for this test, f does not have to be differentiable at C. It has to be differentiable everywhere else. Okay, that's a kind of technicality I'm talking about, which I will not repeat here. Okay, because it's very rare that you encounter that kind of an exception. Anyway, if f is differentiable and if C happens to be a critical point on I, which means that the derivative must be 0, okay, then here is what you can conclude, right? Now imagine the derivative is 0 at this point, okay? So there's a horizontal tangent, perhaps, a sharp corner, just like we saw right here, that's a possibility if, f is differentiable everywhere else except at C. But anyway, either way, what happens is, if, just let me explain this before I write formally the statement of the theorem. If the function is increasing up until this point and decreasing after that, what can you conclude about this point? Of course, it must be a relative maximum, right? And that's exactly what it says. If f has, I guess I should say, if f has, if f prime changes from positive to negative at C. Okay, so this is a situation, positive before C, negative after C. Then guess what? F has a local maximum at C. All right, not hard to understand, right? In fact, it's pretty easy and intuitive, obvious maybe in a sense. In other words, if the function is increasing up until this point and stops increasing and it starts to decrease, what is that? Well, it's the highest point. So it must be highest point in the interval. So it must be a local maximum. It could be absolute maximum. But the first derivative test is a local theorem, which means it only refers to local maximum or local minimum. We don't know much about the universal or global or absolute maximum or minimum. All right, so if f prime changes from negative to positive at C, of course, that's the other way around. decreasing up until C, and 0 at C, the derivative is 0 at C, and then starts to increase, the derivative goes from negative to positive. Then you can safely assume that f has a local minimum at C. All right, so this is known as the first derivative test. Again, it must be pretty obvious, right? And so the pictures are here. You can look at this and it should make sense. All right, now, so to do all of these, you have to figure out what happens before and after the critical point, right? And so to do this, all right, I'm kind of afraid to say this because many people seems to not like this idea. But chart sign, what you would need to construct, or what you should construct, is this thing called the sign chart. Okay, what in the world is a sign chart? The sign chart is a table or a chart with positives and negatives with a number line on the top. All right, let me explain what I mean by this. And the sign chart should be something that you saw perhaps in pre-calculus class or college algebra or intermediate algebra class, when you're trying to figure out in what interval is the function positive or negative. Okay, in this case, the function I'm talking about is, of course, the derivative, because you are trying to figure out what happens to the derivative. Does the derivative goes from positive to negative or negative to positive? And by the way, if the sign does not change, okay, if the sign does not change, like in this, at this point here, it goes from positive 0 to positive, right? If that happens, then we don't know much about that. In fact, it's not a local maximum or minimum. All right, so here's an example. X cubed minus 3x squared minus 9x minus 1. And because we are studying about local max and local min and the shapes of these curves, this will help us, the derivative and the second derivative will help us, sort of sketch graphs, okay? And that's the whole point of this part of chapter 4. All right, you take the derivative, because that's what we want to study, 3x squared minus 6x minus 9. All right, you can factor this. You can take out 3, x squared minus 2x minus 3. You can also factor this into x minus 3 and x minus 1. Would it work? No, of course it doesn't work. To make the middle term -2, you have to have this as a plus. Okay, so I think you can tell if this is equal to 0, that means x must be -1 and 3. These are the roots or the solutions to the derivative, right? The derivative is equal to 0 whenever x is -1 or 3. And in fact, those are the only two zeros, meaning that those are the only two critical values. And the derivative is defined everywhere because it's a polynomial function. It's differentiable everywhere. And we have found exactly 2 critical points. Okay, so here's how the sign chart works. Let's erase that. I want to have a straight line here. Yeah. Now, there are different ways of doing the sign chart. I personally think it's best if you draw a number line. Okay, this is a number line, and then you have -1 and 3, and then you have divided, or you have partitioned the entire number line into 3 intervals from -infinity. Well, I'm not going to write -infinity here. -infinity to -1, and then from -1 to 3, and then from 3 to infinity. And at each point, okay, you see how this is your derivative. So 3x plus 1, you can just divide this into 2, or maybe even 3. The number 3 is positive, so it really doesn't matter. You can even erase this if you don't worry about this, because this doesn't affect the sign of the derivative, right? But since we want to make this complete, I guess we can just go ahead and write this. So the derivative is going to be the first row times the second row, okay? Let's draw that. And then, let's make it nice. Okay, now for each interval, we are going to consider the sign of each of these factors. 3 times, again, you don't have to worry too much about this, but x plus 1 is negative here whenever x is less than negative 1. As soon as x becomes negative 1, of course, it becomes 0. Now, many people don't put this in here. Okay, let me tell you how most people construct their sign charts, right? And then they go between negative 1 and 3. Here, x plus 1 is going to be positive. Okay, plug in numbers like 0 or 1 or 2, any number between here and here, and you will see that x plus 1 will be positive. And of course, any number 3 or bigger is going to still keep this positive, right? Now, this is how most people do the sign chart. I personally think it's a great idea to also include what happens right at these boundary points. Negative 1, that's when x plus 1 is 0, right? And then at 3, what happens? Well, 3 plus 1 is positive. So this is my version of the sign chart. So I will have either negative, 0, or positive at every segment, every interval, as well as these points, which we found to be critical points. Okay, so now do the same thing for x minus 3. That's negative here. When x is negative 1, that's clearly negative. When x is between negative 1 and 3, that's still negative. When x is 3, this becomes 0. And after that, it's positive. Typically, for each row, what you will see is this pattern that goes from negative to 0 to positive, negative to 0 to positive. Okay, and at the bottom, you multiply these. This times this is, of course, our derivative, right? Negative times negative is, of course, positive. And then 0 times negative is 0, right at this point, right? And then positive times negative is negative. That's 0, and this is positive. Okay, and so another thing I would like to do, I personally like to do, and many other people and books don't seem to like doing this, but I think it's a great idea. And that is because I want this to help me visualize this. I want to just draw like a rough sketch of the graph. I know that when the derivative is positive, it increases, all right? And then 0, and then starts to decrease. Okay, so now it's time to apply, and then from here, it goes to 0 and then positive. Now we can apply the first derivative test. You see how that can be done? Because at this point, all right, at negative 1, the function goes from increasing to decreasing. In other words, the derivative goes from positive to negative, where negative 1 is a critical point where the derivative is 0. This has to be a local maximum. Now at 3, the derivative goes from negative to positive. In other words, the function goes from decreasing to increasing. So this must be local minimum. Okay, so the sign chart makes it clear, and these arrows at the bottom for me and for you, I'm sure, will make it even clearer that this is a local maximum and this is local minimum. All right, so I'm going to conclude here. F has a local maximum at negative 1 and a local minimum at 3. Do you know what else I can say with confidence? And this is a powerful statement. I think it should be more emphasized more. No other local extrema. Now, how am I so sure? If somebody says, no, look, after many hours of investigation, I found another local maximum. And that happens at when x is 4025. And I said, no, it's not possible because I have found all of the critical points. And I know that every local extrema has to happen at a critical point, okay? And so I have exhausted the list of all the critical points, namely 2, and I have found what happens to the graph at each of those. And so there are absolutely no other local extrema, period. See how confidently you can state things like this in mathematics. That is beautiful. And by the way, the graph actually does go like this. Okay, if you look at this, and this is where x is negative 1, and this is where x is -3, and the graph is a third degree polynomial, so the end behavior is also correct. It goes up this way and goes down this way. All right, wonderful. All right, here's another example. This time it's a little more challenging, I think. 5x to the 1/3 minus x to the 5/3. Ooh, okay. So you may notice that it's an odd function, and it may be helpful for you to know that it's an odd function. How do you know it's an odd function? Well, it's a cubed function and raised to the first and the fifth powers, for each of these terms. And so, if x is reversed to negative x, then both of these will become negative, meaning that f of negative x is going to be negative f of x. And so that's the characteristic of an odd function. All right, let's take the derivative so we can see when the function is increasing and decreasing. This is 5/3 x to the -2/3 minus 5/3 x to the 2/3. And so this is, let's factor out 5/3. And so you have x to the -2/3 minus x to the 2/3. Okay, so what do you know about this thing here? Well, here, okay, let's, this is a little tricky, right? F is not, let's make an observation. F is not defined. Well, no, F is actually defined at every place. F is defined at every x, the real value x, but F prime is not defined at x equals 0, precisely because of this term here. This is 1 over x to the 2/3, which becomes 1 over 0. That's a bad word to say. When x is 0, right? So the derivative is not defined. It's not differentiable at 0. So that is a critical point. All right, and then what's going to happen? So, well, what can you do? Any critical points besides this? All right, so we can try to set this equal to 0, which means negative to, you know what, let's go ahead and write this as 1 over x to the 2/3. You want this to be equal to x to the 2/3, okay? So we have already established that 0 is a critical point because the derivative does not exist. So assume, to find other ones, assume x is not equal to 0 so that this makes sense. Now you can multiply both sides by x to the 2/3, right? So multiply both sides by x to the 2/3 like this. Okay, and now I'm not gonna write this because it becomes confusing. Maybe I should write down. All right, so if x is not 0, multiply both sides by x to the 2/3, and you get 1 is equal to x to the 4/3. Now, if you take the cube root of this number and take it to the 4th root, you get 1, okay? How many numbers are there? There are 2 of these numbers, plus and minus 1, okay? -1 to the cube root of -1 is -1. And if you take it to the 4th root, that's 1. And of course, 1, the cube root of 1 is 1, and the 4th power of that is also 1. Okay, so we have found all the critical points of this. Okay, so the -1, +1, and -1 ends up here. Maybe I should just list. Okay, all the critical points of f are 1, -1, and 0. Okay, so that's what we have discovered. And anything that maximum, minimum, these kind of things would happen at one of these 3 points. Okay. Now the reason I wrote everything on the left-hand side is because I want to do the sign chart on the right-hand side of this. Okay, so I have -1, 0, and +1, right? This one is slightly, what's a little more, it's trickier because, well, you know, I just have this. Okay, so how do you write the derivative of this thing here? You have, see, I don't have a factor thing in here, right? So it's 5/3 and then 1 over x to the 2/3 minus x to the 2/3. Okay, I need to move these away from this. So let's say this is -1, this is 0, and this is +1. Okay, and I don't need, yeah, I need to make a little adjustment so I have enough space here. All right, so what happens, and this is going to be a little more challenging because you don't have factored forms. Try to plug in numbers like -10 or -1,000 or something. Okay, so what happens is this is going to be a very small number when you plug in -100 or something, or -1,000. Okay, and then this will be, of course, negative. Well, actually, it's going to be this is going to be a positive number, right? Because of the square, right? So over here, you will see that the derivative is going to be negative. Okay, actually plugging in a number in this interval is probably a good thing. So you will have a small number close to 0 minus very large number. And so this part will become very negative, making the derivative negative. Now, when you plug in -1, well, you know that this is going to be 0 because we have figured that, I mean, why do we know that the -1 is a critical point? Because we set inside of this equal to 0 to find it. And in fact, the same thing here too. When x is 1, the derivative will be 0. And now plug in a number here. So these are numbers like -100 or -1/10 or something like that, or -0.5. All right, that's a little tricky because this number will be bigger than 1 when you have, -5, the cube root of -5, and square it. That's going to be a number like minus, I don't know, 0.2 or something. 1 divided by that, that's going to give you a large number here. This number will stay small, a large number minus a small number, and that's going to be a positive number. And when x is 0, what did we say? It's undefined. So you can put U for undefined, or undefined, UND for undefined. All right, plug in a number here. Okay. We actually know what happens because it's an odd function. When you plug in a number like 0.2 or 0.3 or 0.1 or something, this will become large, this becomes small, right? And so it's still going to be positive, okay? And the fact that it's an odd function tells you that as well. And then after this, 1 bigger than 1, like 3 or 5 or 5,000 or a million, this will become very small positive number, and this will become very large positive number. A small number minus a large number is a negative. Okay, so roughly speaking, the graph goes like this: this, that, and undefined here, and then positive and negative. Okay, so what is going on here? And by the way, this is undefined because what happens is, all right, so this number becomes infinitely big, right? As x gets closer and closer to 0, this number becomes, it blows up to infinity. So there's an infinite derivative here, which sort of means that you have a vertical tangent, okay? And so the graph is going to look like this, and then goes up, and you have that infinite tangent, or I should say a tangent with an infinite slope, which is vertical tangent, and then still increasing, and then eventually decreasing, okay? So this is the shape of the graph. This happens when the x is -1. This happens when x is +1. And so you can fairly assume again, or you can certainly assume, because of the first derivative test, that when x is -1, the graph, the function, or the derivative goes from negative to positive. So f has a local minimum at -1 and a local maximum at +1. Okay. And what's happening in 0 is neither maximum or minimum, because this is where the derivative becomes infinitely big. meaning that you have a vertical tangent. And that's why the derivative does not exist, because it approaches infinity. Okay, so the graph is, again, the shape of the graph is here. And if you are to graph this function, I would encourage you to do this on, on your graphing calculator or a calculator app, and you will see certainly see a function that looks, or that is shaped this way. All right, so I'm going to stop here as at the end of part 1. We will still have to go back and talk about the second derivative, concavity, and the points of inflection. All right, so that would appear in the second portion of our video lecture for section 4.5.